Hello, my name is Hazel Cowboy from Langley High School, and this is my project on the effect of temperature on a tardigrade's ability to enter cryptobiosis. To begin, I would first like to address the purpose of this project, which is to know what tardigrades' limits to temperatures are, because it can provide insight into how effective tardigrades will be in battling the onslaught of challenges that will come with global warming. This will also foreshadow how other species will be impacted by temperature changes and how the world will adapt to new global climates. By the end, this project will hopefully prove that tardigrades are extremely competent at adapting to new environments, which will hopefully be a benefit to society by demonstrating the possible limits and temperature restrictions that even the most hardy animals may have. My hypothesis is that if the temperature in the tardigrade's environment is colder, then the tardigrades will be more likely to enter cryobiosis or TUN, because the second most common way for a tardigrade to enter cryobiosis is through TUN. In this form, the animal will only enter cryptobiosis when the environment is below the cell's freezing point. This process allows an orderly transition into cryobiosis, and they may begin to suppress the nucleation of ice crystals, resulting in an ice crystal form that is favorable for subsequent revival and thawing. Some recent advancements in this field have also shown that tardigrades can withstand up to 57 degrees Celsius. As such, starting at this temperature would be ideal. As you can see in this picture, there are different life cycles of the tardigrade. The bottom part of the graph shows the different parts of cryptobiosis, and in this project we'll be examining cryobiosis, or TUN, in which induced proteins disrupt ice crystallization as TUN forms. Throughout this project, I changed the temperature in the experimented petri dishes 11 degrees in each experiment. In order to do that, I added 3 milliliters of increasingly warm water, or ice, to each petri dish except the constants. In order to ensure that each petri dish was affected similarly by sunlight, I set them up in orderly lines with a constant in each row. After observing the changes in this experiment for months, along with witnessing the characteristics of the constants, I have been able to determine that the tardigrades are very sensitive to cooler temperatures. You can see in these pictures a graph of the different temperatures I used, and to maintain the specific low temperatures, I put them into a styrofoam cooler to keep them at that temperature. And then this picture on the bottom is a picture of the different petri dishes set up for the first experiment. Now on to my results. The characteristics of the tardigrades to be very sensitive to cooler temperatures can be observed in the graph average time in cryptobiosis up here in the upper right corner, which details the average time each tardigrade spent at that temperature. At negative 97 degrees Celsius, the tardigrade spent an average of 9.9 hours in cryptobiosis. Additionally, a unique change occurred between the temperatures of negative 75 and negative 64 degrees Celsius, where the tardigrades went from an average of 2.3 hours in cryptobiosis to an average of 0 hours in cryptobiosis. This means at temperatures of negative 64 and above, the tardigrades are only marginally effective at entering cryptobiosis, despite being quite lethargic at higher temperatures. These results indicate that because the tardigrades are only marginally effective at entering cryptobiosis at higher temperatures, negative 64 and below, they're better at. Specifically, between 46 and 57 degrees, they struggle at the most. They were unable to enter the state of self-preservation, and tardigrades became more lethargic in these higher temperatures. Because tardigrades are better at thwarting possibly life-threatening conditions while in cryptobiosis, and they struggle to do so in high temperatures, they may become more vulnerable as temperatures rise due to climate change. I would also like to mention that throughout this project, though this project had largely sound results, there is possible margin for error as these creatures are extremely tiny. And though I checked each petri dish multiple times through a microscope, it is possible that there could be multiple tardigrades in one petri dish. Furthermore, because of a lack of time, the temperature shifts between each experiment was widened, so this project could cover wider ranges of temperatures. Now finally on to my conclusion. This project uncovered a weakness of the tardigrade to extended heat exposure, which will make them vulnerable to climate change. Unless we begin to work on our contribution to end climate change now, tardigrades on this planet will be at tremendous risk. The tardigrades help remove CO2 from the air by fertilizing plants. They also eat algae, which helps keep dangerous algae blooms in control. In order to contribute to continued survival of these creatures, along with future generations of human beings, there are many actions we can take to stifle the effects of climate change, including planting more trees, driving an electric car, etc. Scan the QR code below to learn more about practical actions you can take to combat climate change. Thank you so much for your time today, and these are the references that I utilized. Thank you.